Hi everyone! Today we're going to be finishing up our discussion on waves by quickly reviewing internal waves and then going into more depth with rotational waves. We'll be discussing both coastal and equatorial Kelvin waves, and then finish up with Rossby waves. Okay, so we talked about internal waves briefly in the last lecture, and Group 6 presented the internal wave demo in class on Thursday. Just to quickly review, internal waves are forced internally and occur on the interface between two different density layers. They are very similar to surface waves, except they travel much slower. In deep water, which means that both h1 and h2 are much larger than the wavelength, our phase speed can be written as below. There are two different types of shallow water waves. The first scenario is that h1 is very small, much smaller than the wavelength, such that the wave propagates just below the surface of the water and h2 is larger than the wavelength. In this case, the phase speed is the square root of g prime h1, where g prime is shown below. The second case is that both h1 and h2 are much less than the wavelength, such that the wave propagates in very shallow water right below the surface. The phase speed in this case is equal to the square root of g prime times h1 h2 over h1 plus h2. We also talked about the scenario of continuous stratification, where our dispersion relation is shown below. And we importantly noted that in this case, and more generally in the real ocean, waves propagate both horizontally and vertically. At the end of the last lecture, we quickly discussed that when the frequency becomes small enough, or the wave period long enough or large enough, the rotation of the Earth becomes important, and we need to consider the Coriolis force on our waves. So for internal waves, we need to include F in our dispersion relationship below. These waves are called inertial rotational waves. For shallow water surface waves with rotation, our first wave that we're going to talk about is called a Poincare wave. Poincare waves propagate in any direction. The frequency is always larger than the Coriolis force, F. They are almost always dispersive, except for the case when the frequency is much larger than F. And finally, fluid parcels generally tend to travel in horizontal elliptical orbits. The dispersion relationship for Poincare waves is shown here. Sigma squared is equal to F squared plus GHK squared. The dispersion relationship can be visualized using something we call a dispersion diagram, which has wave number k on the x-axis and frequency sigma on the y-axis. And we simply plot the dispersion relationship. In the case of Poincare waves, the dispersion diagram looks like this. There are two limits that are relevant for Poincare waves. The first is up here. At this spot, F squared is much smaller than GHK squared, or k to the negative 1 is much less than the square root of GH over F squared. In this case, we can neglect our F term because it is so much smaller and our dispersion relation simplifies. Now, the parcel travels horizontally back and forth, just like a regular surface gravity wave. The other limit of a Poincare wave is down here, where f squared is much larger than GHK squared. In this case, k to the negative 1 is much larger than the square root of GH over f squared. Our dispersion relationship is simplified as shown below. And these parcels simply travel in horizontal circles like inertial circles. Here's a figure of the dispersion relationship, which summarizes a little bit more what I was just talking about. Now, you might notice that this number, the square root of GH over f squared, is important here. This number is called the Rossby radius of deformation, and we use RD to represent this. The Rossby radius of deformation is the distance that a particle or wave travels before being significantly affected by Earth's rotation. Note that the radius of deformation decreases with latitude because f increases. So a wave at high latitude travels only a short distance before being affected by the rotation of the Earth. Now quickly recall that k is equal to 2 pi over lambda. So the above limits for Poincare waves can be simplified as shown here. Wavelength much greater than 2 pi times the radius of deformation will give us near inertial circles. Similarly, a wavelength much less than 2 pi times RD will give us surface gravity waves. Okay, so those are Poincare waves. We are now going to switch over and continue our discussion of rotational waves and talk about Kelvin waves. There are two types of Kelvin waves. The first is a coastal Kelvin wave. A coastal Kelvin wave is a balance of the Coriolis force against topography, or really the coastline. In the northern hemisphere, think of a wave moving northward along the coast, with the coastline on the right-hand side. This wave is deflected to the right due to the rotation of the Earth. However, the coastline on the right prevents the wave from turning right, and instead causes water to pile up on the coast. The pile of water creates a pressure gradient directed offshore, and a geostrophic current directed northward. We note that coastal Kelvin waves always propagate with the shoreline on the right in the northern hemisphere, and propagate with the shoreline on the left in the southern hemisphere. Take a minute to think about this and make sure it makes sense to you. The amplitude of Kelvin waves is negligible at a distance offshore given by the square root of GH over F, which we note is the Rossby radius of deformation. This means that coastal Kelvin waves appear trapped close to the coast because they rapidly decay away from the coast and are negligible at a distance given by the radius of deformation. For Kelvin waves traveling at the surface, this distance is about 200 kilometers. The other type of Kelvin wave is an equatorial Kelvin wave. An equatorial Kelvin wave is a balance between the Coriolis in the northern hemisphere and the Coriolis in the southern hemisphere, or its southern counterpart. An equatorial Kelvin wave is often excited by an abrupt change in the overlying wind field, which is often a shift in the trade winds associated with El Niño. and we'll discuss that a little bit more in class next week. Equatorial Kelvin waves must travel eastward. Think about why this might be for a minute. Another property of equatorial Kelvin waves is that they have speeds slow enough to give a Rossby radius of deformation on the order of 250 meters. And as such, these special types of Kelvin waves often appear to be trapped close to the equator. And finally, we'll take a look at the dispersion relationship for Kelvin waves. Kelvin waves are non-dispersive and have a frequency of k square root gh, which gives us a phase speed of square root gh, which we note is the same as shallow water surface gravity waves. We can plot this in our dispersion diagram, and we note a linear relationship between wave number and frequency, again, like surface gravity waves. Note that we only include positive wave number for Kelvin wave, because where k is positive, the phase speed is east. And where the slope or the group speed is positive, CG is also east. We notice that both phase speed and group speed are east for Kelvin waves. Here's sort of our classic schematic of how Kelvin waves propagate, and then interact with the coastline with waves propagating north in the northern hemisphere and south in the southern hemisphere. Okay, so we'll finish up our discussion on waves by talking about Rossby waves. Rossby waves are wicked cool. They're huge, they're undulating, they're slowly propagating waves that routinely cross the entire ocean basins. In the ocean, Rossby waves play an important role in El Nino, and in the atmosphere, Rossby waves generate the huge meanders of the jet stream. Rossby waves occur due to conservation of potential vorticity and the beta effect, which again, PV is equal to F plus the relative vorticity over the water column H, or the height of the water column H. And beta is defined as the change in Coriolis force F with respect to latitude. So, Rossby waves occur when water is displaced north or south of its original position. Let's say here we have our east to west line of water with no relative vorticity. And we'll put the equator down at the bottom for simplicity. We'll say we're in the northern hemisphere. Our surface waters are displaced as such. Now, again, we need to conserve potential vorticity here, such that our derivative of PV with respect to time is equal to 0. So if we pick this point, we'll label it A, and as a result of the displacement, the latitude of the water parcel has increased. So F has increased. To conserve PV, the water parcel must gain negative relative vorticity. So at point A, our vorticity will be acting in the clockwise direction. This will act to move fluid south. Similarly, at point B, F decreases, so we have to gain positive relative vorticity, and this will act to move fluid to the north. We can use the same reasoning at other points as such, and we find that this wave will propagate to the left, or to the west. This is true of all Rossby waves, as they always propagate to the west. Our dispersion relationship for Rossby waves is shown here, along with the dispersion diagram. In this case, we note that kx is always less than 0, meaning that we have a westward propagation. So our phase speed, or our phase velocity, is always west. For short waves, those that the absolute value of 1 over kx is less than the Rossby wave of deformation, or Rossby radius of deformation, the slope of the dispersion relation is positive, meaning that the phase speed is positive or eastward. On the other hand, for long waves, those that the absolute value of 1 over kx is greater than the Rossby radius of deformation, the slope of the dispersion relation is negative, and our group speed is westward. For very long waves, those that 1 over kx is much greater than Rd, Rossby group speed is still westward, but in this case, waves are non-dispersive. Okay, that's all I have for you guys for this lecture. Here is the summary of the dispersion relationships we saw in class on Thursday, and now we have covered all of the waves here. Please note that we will not make you memorize dispersion relationships, but you should generally know how we have discussed each type of relationship in the context of the class and know what the dispersion diagram looks like. Due for Tuesday, there's a short and fairly easy forum to complete about this lecture, and don't forget homework 5 is also due on Tuesday. Other than that, I hope you guys have a good Thanksgiving break, and we will see you next week. As always, let me know if you have any questions. Thanks, guys.